Hello, math learners! Our lesson for today is about trigonometric equations and polar coordinate system. The learning objectives are you are going to recall inverse trigonometric functions, locate points in polar coordinate system, solve trigonometric equations, convert the coordinates of a point from rectangular to polar systems, and vice versa. This is the Learning Pocket concept map. We are going to have trigonometric equations and its applications. Then, polar coordinate system, we are going to have the conversion as well as the graph. Let us start first with trigonometric equations. Trigonometric equations are equations involving trigonometric functions of unknown angles. The solutions to a trigonometric equation are values of the angle which satisfy the equation. All possible values which satisfy the given trigonometric equation are called solutions of the given trigonometric equation. The solutions of these equations for a trigonometric function in variable x, where x lies in between 0 and 2 pi, is called as principal solution. If the solution contains the integer n in it, it is called as the general solution. Let us have an example. Find the principal solutions of the given equation sin x is equal to the square root of 3 over 2, wherein x is between 0 and 2 pi. For the solutions, you write first the given sin x is equal to square root of 3 over 2, and this is now x is equal to sine to the negative of 1 square root of 3 over 2. Meaning you have to find the value of the angle x using the inverse trigonometric function. And using the unit circle, we have quadrant 1 having sine equivalent to square root of 3 over 2, in which the angle is pi over 3. And in quadrant 2, we also have square root of 3 over 2, which is the value of y or the sine function. Therefore, x is equal to pi over 3 and 2 pi over 3. Therefore, the principal solutions are x is equal to pi over 3 and x is equal to 2 pi over 3, or can be written as the set of x such that x is equal to pi over 3 and 2 pi over 3. Using the calculator, you can use the radian mode. Then you press shift sign square root of 3 over 2 equals, then it will display pi over 3, which is a reference angle. And then to find the angle, so in the second quadrant, the angle is 2 pi over 3. Again, only in quadrant 1 and quadrant 2 wherein sign is positive. And we have to use inverse trigonometric functions in finding the measure of the angle. If the given interval is in terms of radians, then your answer should be also in radians. Next, example 2. Solve 1 plus cosine theta is equal to 3 cosine theta, wherein theta is between 0 and 360 degrees. For the solutions, so you copy first the given and you transpose 1 to the other side, it will become negative 1, and transpose 3 cosine theta to the left side, then we have negative 3 cosine theta. And then you simplify, we have negative 2 cosine theta. Negative 3 plus 1 cosine theta is negative 2 cosine theta equals to negative 1. And then divide by a negative 2, divide also the other side by a negative 2. We will have now negative 1 over negative 2. Then simplify, we can have positive 1/2. Then to find the value of theta, we are going to use the inverse trigonometric function. So this is now theta is equal to r cosine 1/2, or we can write in cosine to the negative of 1, 1/2. Therefore, the measure of the angle is 60 degrees in the first quadrant, or you can have 300 degrees in the fourth quadrant. Again, the solution to the given trigonometric equation is the set of theta such that theta is equal to 60 degrees and 360 degrees. Using the calculator, you have to press shift cosine 1/2 equals, then it will display 60 degrees. And for cosine, we can have only positive cosine in the first quadrant as well as in the fourth quadrant. Take note, the interval is in terms of degrees, which means the answer should be in degrees. If the unknown will not be limited to the principal values or principal solutions, then the solutions to 1 plus cosine theta is equal to 3 cosine theta should be expressed as general solutions. That is, theta is equal to 60 degrees plus 360 times n. N will represent any integer and also the number of revolutions. Or you can have theta is equal to 300 degrees plus 360 degrees n. Next, example number 3. Solve cosine squared x plus cosine x minus 2 is equal to 0. For the solutions, you copy first the given, and then you can factor the trinomial. The factors of cosine squared x, we have cosine x and cosine x. Factors of negative 2, we have positive 2 and negative 1. And when you multiply 2 and cosine x, we have 2 cosine x. Cosine with negative 1 is negative cosine x. So, when you combine, it will give you the middle term, which is cosine x. And then, we have to equate each factor to 0. So, let's work first with the first factor. We have cosine x plus 2 equals to 0. So, cosine x is equal to negative 2. And x is equal to cosine to the negative 1, 2 has no solution. Then, let's work with the second factor. Cosine x minus 1 is equal to 0. Transpose negative 1, we have positive 1. And to solve for x, x now is equal to cosine to the negative 1, 1. So, the value is x is equal to 0 degree and x is equal to 360 degrees. Or, you may write in radian, x is equal to 0 and x is equal to 2 pi. Therefore, the solution of cosine squared x plus cosine x minus 2 equals 0 is the set of x such that x is equal to 0 and 2 pi. Or, the set of x such that x is equal to 0 degree and 360 degrees. Take note, if the interval is not given, you may write your answer in degrees or in radian. Example number 4. Solve for the principal solutions. Given 2 cotangent squared A plus cosecant squared A equals 2. For the solutions, you have to express the equation in terms of a single function. Since cosecant squared A equals 1 plus cotangent squared A, then 2 cotangent squared A cosecant squared A equals 2. This is the given. Then, we can substitute 1 plus cotangent squared A to cosecant squared A. Then after this, you simplify 2 plus cotangent square A, 2 plus 1 cotangent squared A is equal to 3 cotangent squared A. Then transpose 1, so 2 minus 1. Then we have 3 cotangent squared A is equal to 1. And divide each side by 3. So we will have cotangent squared A equals 1/3. Then find the value of A. Cotangent A is equal to positive or negative square root of 1/3. So meaning you have to extract the square root of both sides to have cotangent A here. This expression will give us 1 over square root of 3. And we have to rationalize the denominator by multiplying square root of 3 over square root of 3. Then we can have square root of 3 over 3. You may use the calculator to find the value of A. You can use the degree mode, then press shift tan square root of 3 over 3. Then, since this is cotangent, you press the inverse. You press the reciprocal key, then equals, then it will display 60. Then, for a negative square root of 3 over 3, press shift tan negative square root of 3 over 3, then the reciprocal key equals, then it will display negative 60, and negative 60 is equivalent to 300 degrees. So here, for a positive square root of 3 over 3, A is 60, or you can have also 240. Because cotangent A is positive in quadrant 1 and in quadrant 3 with this value. Then if cotangent A is equal to negative square root of 3 over 3, then angle A is equal to 120 degrees, that is in the second quadrant since the reference angle is 60, or A is equal to 300 degrees or negative 60. Again, cotangent is negative in the second quadrant and in quadrant 4. Therefore, the principal solution set to cotangent squared A plus cosecant squared A equals 2 is the set of A's such that A is equal to 60 degrees, 240 degrees, 120 degrees, and 300 degrees. Next example. Solve cosine B plus sine B equals 1. The interval is between 0 and 2 pi. For the solutions, copy first the given cosine B plus sine B equals 1. Then, you may transpose sine B to the other side. So we have now cosine B is equal to 1 minus sine B. Then, you can expand the expression by squaring both sides. So we have now the square of cosine B equals the square of 1 minus sine B. Then, you can expand the other side. That is equivalent to 1 minus 2 sine B plus sine squared B. That is, the square of 1 is 1. 1 times negative sine B times 2 is negative 2 sine B. Sine B times sine B is sine squared B. And then, you can apply the Pythagorean identity. Cosine B squared is equivalent to cosine squared B, which is equal to 1 minus sine squared B. and copy the right side. And by this time, you can transpose 1. So we have here negative 1. Then combine. So what we have is 1 minus 1 is 0. So what is left is negative 2 sine b plus sine squared b. And then you can transpose the two terms here to the other side and combine it with negative sine squared b and equate it to 0. So what we have now is 2 sine b minus 2 sine squared b equals 0. Then factor this. We have 2 sine b times 1 minus sine b. That is, this is the common factor. So 2 sine b divided by 2 sine b is 1. Negative 2 sine squared b divided by 2 sine b is sine b. And then equate each factor to 0. So you have 2 sine b equals to 0. Divide this by 2. So sine b is equal to 0. And to find the value of angle B, use the inverse trigonometric function. So sine to the negative 1 equals 0. So B is equal to 0, or you can have B is equal to 2 pi. And for the second factor, 1 minus sine B, equate it to 0. So we have 1 minus sine B equals 0. So transpose 1, sine b is equal to 1. Then use the inverse trigonometric function to solve for b. Then we have arc sine 1, or b is equal to sine to the negative 1 of 1. So b is equal to pi over 2. Therefore, the solution to the equation cosine b plus sine b is equal to 1 is the set of b such that b is equal to 0, 2 pi, and pi over 2. Next, let us have the applications of trigonometric equations. The problem is, one of the cables that anchors the center of the Ferris wheel to the ground must be replaced. The center of the Ferris wheel is 69.5 meters above the ground, and the second anchor on the ground is 23 meters from the base of the Ferris wheel. How long is the cable, and what is the angle of elevation from ground up to the center of the Ferris wheel? So this is an image of a Ferris wheel, and this side, we consider this as the y, which is equivalent to 69.5 meters. And this is the opposite side of the given angle. And this is the base now, 23. We label this as x. This is the adjacent side of the angle. So for the solutions, first, find the length of the cable using the Pythagorean theorem, or we call this also as the equation of the circle. So replace 23m to x, 69.5m to y, and then square each. Then the result now is 5,359.25 meters squared. Then we have to extract the square root of 5,359.25 meters squared. So R is equal to 73.2 m. So this side, which we represent by R, or the hypotenuse, is equivalent to 73.2 meters. Next, we have to find the angle using the tangent function, and you have to round off to 2 decimal places. Tangent function is tangent theta is equal to the opposite side of theta over the adjacent side of theta. And the opposite side is 69.5 over 23. So 69.5 over 23 is 3.02173913. Then we have to solve for theta using the inverse trigonometric function. So we have tan to the negative 1 of 3.02173913. So theta is equivalent to 71.7 degrees. Therefore, the angle of elevation is 71.7 degrees and the length of the cable is 73.2 meters. Next, example 2. At 57 feet from the base of a building, you need to look up at 55 degrees to see the top of a building. What is the height of the building? Supposing this is the building and this is the angle equivalent to 55 degrees. From the foot of the building to this point, we have 57 feet. This is the adjacent side, while this is the opposite side. So for the solution, tangent theta is equal to opposite side of the theta over the adjacent side of theta. The opposite side is unknown, so we are going to represent it by h, which is the height, over the adjacent is 57. And when we cross multiply tan 55 degrees times 57, so we have now h is equal to 57 times tan 55 degrees. And multiply 57 by tan 55 degrees, we have 81.4 feet. So the height is 81.4 feet. Or you can use also the cotangent function. Cotangent theta is equal to the adjacent side of theta over opposite side of theta. So we have cotangent 55 degrees is equal to the adjacent is 57 over the opposite, which is h. Then cross multiply, we have now h times cotangent 55 degrees equals 57. And then we have to divide both sides by cotangent 55. So we have h is equal to 57 over cotangent 55 degrees. So we still have the same answer, 81.4 feet. Therefore, the height of the building is 81.4 feet, whether you're using the tangent function or the cotangent function. Let us have now the polar coordinate system. The polar coordinate system is a two-dimensional coordinate system in which each point on a plane is determined by a distance from a reference point and an angle from a reference direction. Let us have first key terms. In this illustration, this is now what we call the pole. This one is the radial distance. The angle is the polar angle, and this axis is the polar axis. Pole is the reference point of the polar graph, and this is analogous to the origin of the Cartesian coordinate system. Polar axis is the ray from the pole in the reference direction. Radial distance, or we called it as radial coordinate or simply radius, is the distance from the pole. The radial coordinate is often denoted by r. Polar angle, or we call it as angular coordinate or azimuth, is an angle measured from the polar axis, usually counterclockwise, and the angular coordinate is denoted by theta. Angles in polar notation are generally expressed in either degrees or radians. 2 pi radian being equal to 360 degrees. Let us have now converting between polar coordinates and Cartesian coordinates. Polar and Cartesian coordinates can be interconverted using Pythagorean theorem and trigonometry. To convert from polar to rectangular or Cartesian coordinates, we use the following formulas. Cosine theta is equal to x over r, wherein when we cross multiply cosine theta and r, we will have x is equal to r cosine theta. Then sine theta is equal to y over r. Cross multiply, then we will have y is equal to r sine theta. Then to convert from rectangular or Cartesian coordinates to polar, we're going to use these formulas. R squared is equal to x squared plus y squared, and tangent theta is equal to y over x. Let us have polar coordinates to rectangular coordinates. The steps are, first you have to write cosine theta is equal to x over r, which will give us x is equal to r cosine theta, and sine theta is equal to y over r, which will give us y is equal to r sine theta. In this figure, this is the rectangular coordinate system. This point with coordinates xy, which can also be considered as a point with coordinates r and theta. This one is the representation of rectangular coordinates, while this is the representation of the polar coordinates. Then evaluate cosine theta and sine theta. Multiply cosine theta by r to find the x-coordinate of the rectangular form, and multiply sine theta by r to find the y-coordinate of the rectangular form. For example, write the polar coordinates 3 and 45 degrees as rectangular coordinates. For the solutions, you write first r is equal to 3. This is the radial distance, and the angle represented by theta is 45 degrees. First, we have to solve for x is equal to r cosine theta. So, r is 3 and theta is 45 degrees. Then, cosine 45 degrees is equivalent to square root of 2 over 2. Then, times 3 here. And the value now of x is 2.12. Next, we have to solve for y is equal to r sine theta. R is 3, then sine 45 degrees for theta. Sine 45 is again square root of 2 over 2 times 3. Then y is equal to 2.12. Therefore, the rectangular coordinates are 3 square root of 2 over 2 and 3 square root of 2 over 2, or you can express in decimal form 2.12 and 2.12. So using the calculator, you can also get the rectangular coordinates. Now, this steps is based from Casio FX991ES Plus. So press Shift and this symbol, the minus key. Above this is the rectangular coordinate, and it will display rect and the open parentheses, and after that you press 3, then Shift, and you press this key, the comma, and it will display rect open parentheses 3 comma. After that, you press 45 for the 45 degrees. Then close parentheses equals, then it will display x is equal to 2.12132344. And then just move the cursor, then you will find y is equal to 12, 13, 20, 3, 4, 4. So, you can use this solution or you can use the calculator in order to change polar coordinates to rectangular coordinates. Next, let us have rectangular coordinates to polar coordinates. The steps are: solve for the measure of the polar angle using tangent theta is equal to y over x. Then substitute the values of x and y. Then apply inverse trigonometric function to find the measure of the polar angle. And solve for the radial distance using r squared equals x squared plus y squared. Then substitute the values of x and y and then you have to simplify. For example, convert the rectangular coordinates 3 and 3 to polar coordinates. So the value of x is 3 and the value of the y coordinate is also 3. For the solutions, you solve first for the angle represented by theta. So tangent theta is equal to y over x. Substitute 3 to y and 3 to x. So 3 over 3 is 1. In solving for the angle, use the inverse function. So you have tan to the negative 1 of 1. Therefore, theta is pi over 4 or equivalent to 45 degrees. And to solve for r, using r squared is equal to x squared plus y squared. Replace x by 3 and y by 3. So you have 9 plus 9 is 18. Extract the square root. So we have square root of 18. And the answer is 3 times the square root of 3. Or we can change it in decimal, 4.24. Therefore, the polar coordinates are 3 square root of 2 and pi over 4. Or you can express it in decimal, 4.24, and express also the angle in degrees equivalent to 45 degrees. Take note that r squared equals 18 implies r is equal to positive or negative square root of 18. We choose the positive r value since r is the radial distance and distance is always positive. Using the calculator, you can press shift and the positive key. Above this, we have the polar. So it will display pole. Then open parentheses. Then press 3. Then shift. And then the comma key. It will display pole, open parentheses, 3, and comma. And then you have to press 3, close parentheses, equals, it will display r is equal to 4.24, 26, 40, 687. Theta equals 45. And just place degree to indicate the degree measure. Next, let us have plotting points using polar coordinates. The polar grid is scaled as the unit circle with the positive x-axis now viewed as the polar axis and the origin as the pole. The first coordinate r is the radius or length of the directed line segment from the pole. The angle theta indicates the direction of r. We move counterclockwise from the polar axis by an angle of theta and measured a directed line segment the length of r in the direction of theta. Even though we measure theta first and then r, the polar point is written with the r coordinate first. For example, plot the point with polar coordinates 2 and pi over 4 and convert it to rectangular coordinates. So we have to move pi over 4 units in the counterclockwise direction and then a length of 2 from the pole. For the solutions, solve for x is equal to r cosine theta. So x is equal to 2 cosine pi over 4, that is the value of theta, and 2 is the value of r. So it is square root of 2. And in decimal, it is 1.41. Then solve for y equals to r sine theta. So y is equal to 2 sine pi over 4, which is equivalent to square root of 2. And in decimal, 1.41. Therefore, the rectangular coordinates are square root of 2 and square root of 2, or 1.41 and 1.41. Take note, calculator should be in radian mode, or you may convert radian into degree measure. Pi over 4 is just simply equivalent to 45 degrees. Now, this is how to graph. This is the polar grid, scaled 1 to 4. Here, 1 to 4, negative 1 to negative 4, negative 1 to negative 4. From the pole or from the origin, you draw a segment going to this point, which is equivalent to a distance of 2, and this location is equivalent to 45 degrees or pi over 4. And you mark a point, and this point now is the location of the polar coordinate 2 pi over 4. If you are using the coordinate grid, the rectangular coordinates, we have 1.41 and 1.41. So just locate 1.41 for x and 1.41 for y. And the point is exactly located here. Next example, plot the point with polar coordinates 3 and 90 degrees and convert it to rectangular coordinates. So using the calculator in degree mode, press shift, the negative key, 3, shift, the comma key, 90, then close parentheses, then equals, then it will display x is equal to 0 and y is equal to 3. Therefore, the rectangular coordinates are 0, 3. So this is the graph. To locate 390 degrees in the polar grid, you count 1, 2, 3 as the radial distance, and this positive y-axis coincide with the 90 degrees. So you mark a point here, then this is now the point with the coordinates 390 degrees. And using the coordinate grid, count 1, 2, 3 and mark up with a point here, and this is now equivalent to 0, 3 as the equivalent rectangular coordinates of 390 degrees as our polar coordinates. Next, let us use symmetry to graph polar equations. Polar equations can be used to generate unique graphs. The following type of polar equation produces a petal-like shape called a rose curve. Although the graphs look complex, a simple polar equation generates the pattern. The formulas that generate the graph of a rose curve are given by r equals a times cosine n theta, and r is equal to a sine n theta, where a is not equal to 0. And this is now the illustration. For r is equal to a cosine n theta, if n is even, this is the form. If r is equal to a sine n theta and n is odd, you have a 3-petaled rose. For example, Find the symmetry of the rows defined by the polar equation r equals 3 sine 2 theta and create a graph. For the solutions, to graph the polar equation, A. Tabulate values of theta between 0 and pi over 2 or 0 degrees and 90 degrees. So, the table will compose radian or degree measure, radial distance, polar coordinates in radian, polar coordinates in degrees, and then polar equation with the solutions here. So first, let us have 0 degree. So the radial distance is 0. Polar coordinates in radian is 0, 0. The polar coordinates in degrees 0 and 0 degree. Then, using the polar equation r is equal to 3 sine 2 theta. This is now 3 sine 0. 2 times 0 is 0. In which r is equal to 0. So here, 0. Next, for pi over 6 or 30 degrees, the answer is 2.6 or square root of 3 square root of 3 over 2. To get this, we have 3 sine 2 30 degrees, which will give us 3 sine 60 degrees, and this is equivalent to 3 square root of 3 over 2 or 2.6. That is why our polar coordinates in radian is 2.6 pi over 6 or 2.6 30 degrees in polar coordinates in degrees. Then for pi over 4 equals 45, we have R3 because 3 sine 245 is 3 sine 90 and sine 90 is 1 times 3 it's 3. That is why the polar coordinates is 3 pi over 4 or 345 degrees. For pi over 3 or 60 degrees, the value of r is 2.6. For the solution, we have 3 sine 260, which will give us 3 sine 120, in which the value is 3 square root of 3 over 2 or 2.6. That is why the polar coordinates we have 2.6 pi over 3 or 2.6 60 degrees. For pi over 2 or 90 degrees, the value of r is 0. Solution, 3 sine 2 times 90 is equal to 3 sine 180, in which the value of r is equal to 0. So, the polar coordinates, we have 0 pi over 2 or 0, 90 degrees. Next, letter B, you have to plot the polar coordinates. You may use the radian or the degree measure. The 5 polar coordinates give 1 petal of the rose as shown in the graph. So, this 5, 1, 2, 3, 4, 5. So here, 0, 0 for 0 degree. Then you have 3 pi over 4. So it's 1, 2, 3 here, 3. Then pi over 4, the measure of the location is pi over 4. Then 2.6. 2.6 is somewhere here. And then pi over 3. And then pi over 6. This is pi over 6 or equivalent to 30 degrees. Then here 2.6 and pi over 3 because the location here is pi over 3 or this is 60 degrees. And then for 90, that is 0. So 0 again here, pi over 2 or 90. So this is 1 petal of the rose. Next, you have to reflect the image to the other 3 quadrants. Gives the entire graph as shown at the right. So here, this is the first petal. And you draw the same image on the second quadrant, another image on the third quadrant, another on the fourth quadrant, which will give you a 4-petaled rose. So again, to find the symmetry of the rows defined by the polar equation R equals 3 sine 2 theta. And when you're asked to create a graph using the table of values, you can have the radian measure or you can have the degree measure. There are 5 points here. Supposing we're going to add 2 more points in order to have an accurate curve of the petal. So let's add 15 degrees and 75 degrees. 15 degrees is equivalent to pi over 12. 75 degrees is 5 pi over 12. So here, this location and here. Let us have now the point with coordinates 0, 0. Then the point 3 pi over 4. 2.6 pi over 6. 2.6 pi over 3. Then 1.5 5 pi over 12 and 1.5 pi over 12. Then connect the points, you will have a single petal. And you have to reflect the petal to the different quadrants. And you can color your work. Then you have now the 4-petaled rose. This is now the graph of R is equal to 3 sine 2 theta. I will give you more samples. And then for your final graph, all you have to do is to complete the rotation of the measures of the angle. Here are examples of polar equation designs. You may create your own equation and be creative in your designs. Do you have questions? If there is none, see you next time. Bye!